10 reactions.
One where it's just like acid base and then
Conjugate acid, conjugate. Yep, exactly. And that was our Bronsted-Lowry definition of acids and bases, and we can use that to look at conjugate acids and bases.
Are we going to go over that a little bit more today? Or?
I hadn't planned on it. We could certainly go through one or two if you'd like.
I'm good already.
You guys are good?
Are
All
we
right.
doing something new?
Are we doing something new today?
Yeah.
Yes.
That throws me off.
Well, just practice a couple of these tonight, and because we're at a point where we can learn something new, but something new that's not really even like related to that stuff. So we're going to talk about pH today, and I think that pH is a pretty straightforward concept, but I don't know where some of you guys are with math in terms of Algebra 1, Algebra 2, but I'm going to teach you today something about logarithms. And maybe you've heard about them, maybe you haven't, but you don't need a tremendous amount of knowledge. Colonel, where's your notebook?
I don't write down notes.
Okay. I hope you have a photographic memory then.
Close enough.
I'm going to teach you something about logarithms when we need it. But first of all, I want to talk about these types of reactions, or these types of situations, where we have an remember that word for tomorrow, amphoteric substance, a substance that can act as either an acid or a base, and we would get H3O plus OH minus. And we could say, that's the acid, that's the base, that's the conjugate acid, that's the conjugate base. No biggie. We have done that a lot. And again, this process is called auto-ionization. The auto-ionization of, in this case, water. So if I have my bottle of water, or Alan his bottle of water there, most of what we have in that bottle of water is water, but there is a certain amount of hydronium ion, or hydrogen ion, if you want to say it that way, and hydroxide. And there's actually a very tiny amount. Now let me show you how much. I want to remind you, though, of some notation we learned a long time ago. We talked about molarity. And molarity was, moles of solute over liters of solution. And we gave it a symbol. We said, like, if it said, for example, HCl equals 0.025 molar. That bracket there, all that means is molarity of whatever's inside of it. I don't know if you remember that notation or not. If you don't, there it is again. So what we know is at 25 degrees C, I just have, say, water that's between 20 and 25 degrees C, room temperature water. These arrows, when they're written in one facing forward, one facing backward, this means there's something called an equilibrium. Now that equilibrium just means that, it doesn't mean that we have equal amounts of things, it just means that we're going to have a situation where at a certain temperature, I'm going to have definite amounts of each of these things. And the amounts of H3O, hydronium, the concentration of hydronium ion, is 10 to the minus 7 molar, and the concentration of my hydroxide is 10 to the minus 7 molar. So neutral water at room temperature have equal amounts of hydronium ions and hydroxide ions, equal amounts. So in other words, if I had more of that, it would be acidic. If I had more of that, it would be basic, but they're equal. So I need to talk to you about something called logarithms now, because these values help us to establish our pH scale. Now don't be afraid, because I'm going to show you some information that you may not have learned in math class yet. Everybody knows about exponents. So if I have 10 to the a or 7 to the third, this is a base raised to a power. And the act of taking the logarithm of something is sort of the inverse of raising something to a power. So let's say I want to have the log base 10 of some number, like 100. Okay? What this means is, if I want to get that value x, I take 10, raise it to the x, and that gives me 100. So what would your value of x be in that case? 2, yeah. 10 to the 2 is equal to 100. So we would say log base 10 of 100 is equal to 2. How about the log?
Daniel Seneca, please report to room 25.
The log base 10 of 1,000. What's that going to be? What do I raise 10 to get 1,000? Yeah, it's 3. How about this one? Log base 10 of 0.1. What do I raise 10 to get 0.1? -1. Yeah, -1. Good. Good, Colonel. 10 to the -1 is equal to 1 over 10 to the 1, which is 0.1. So this idea of log is pretty simple. You could do logs of other bases as well. Like I could say log base 3 of 27 is equal to what? So 3 raised to some power gives me 27. What would that be? 3, yeah. So the log base 3 of 27 is 3, or 3 to the third is 27. Now, if you have numbers that you can't just do in your head, then you have to use a calculator. For example, log base 10 of 0.7152. I don't know what that is in the top. What do I raise 10 to get 0.07512? Well, you have to use a calculator. So if you have your calculator handy, you should have an LOG button. My LOG button's right there. And I hope everyone has an LOG button. Let me show you. Ooh, my batteries are low. So the way you do this is you hit log, and it doesn't say base 10 on it because LOG log is understood to be base 10 unless you put another number there. So just log and then put your number in there, 0.7152. And the value is -0.146. So if I raise 10 to the -0.146, I get that number. So for our purposes, the log button on our calculator is going to do it all for us. You might be saying, well, how does this relate to pH? Well, I'm going to tell you, and this is certainly something you want in your notes. The negative log base 10 of the concentration of H3O is equal to pH. Another way to write that, if you like, log base 10 of the concentration of hydrogen ion, it means the same thing, is pH. We can also say the negative log base 10 of hydroxide, that gives us something called POH. And that's going to become important a little bit later. So pH, negative log of hydrogen ions, the concentration of hydrogen ions in molarity, concentration of hydronium means the same thing, and then we can also do POH. So let's go over to our water here, and let's calculate the pH of our negative water, of our neutral water. All right, let's get rid of this. So I'm going to take the negative log base 10 of 10 to the minus 7. Well, what do I have to raise 10 to get 10 to the minus 7? That's an easy question. What do I raise 10 to get 10 to the negative minus 10 to the minus 7? Negative 7, right. But if I take the negative of negative 7, I get 7. So the pH of neutral, of water, which is neutral, is 7. So that's where that magical number of 7 comes from. Okay? Now here's a bit more information for you, and it might seem like a lot of information, but if you write it down and we take some time and look over it, I think you'll get it. I'm going to give you some more vocabulary. Strong acids dissociate 100% in solution. And what that means, I'll let you write that down. What that means is that if I have some HCl and I put it in water, if I take HCl, which is a strong acid, I put it in water, it's going to break up 100% into hydrogen ions and chloride ions. So if I say the concentration of HCl is 0.1 molar, that's the same thing as saying the concentration of hydrogen ions is 0.1 molar. Strong bases, something like, oh, let me write here, strong bases, what? Milk? No. Strong bases are things like sodium hydroxide, and we're going to have to test some milk and see if it's acidic or basic. Lye, yeah. Strong base dissociates 100% in solution. So if I have some, say, sodium hydroxide, that's 0.1 molar. Well, that means that I put sodium hydroxide, I get sodium and hydroxide, and that hydroxide would have a concentration of 0.1 molar. Later on, sometime next week, we're going to learn about something called weak acids and weak bases. They don't break up 100%, only a small percentage. Okay, so we could talk about, we have a negative log of the concentration of hydrogen ions is pH, and I told you the negative log of the concentration of hydroxide ions is POH. And there's a very interesting relationship that you should know. Whatever my pH value is plus my POH value, they have to add to 14. It has to add up to 14. Because for any solution of an acid or a base, the concentration of hydrogen ions times the concentration of hydroxide ions has to be 10 to the negative 14. So this is the logarithmic version of it, and this is the actual molarity version. This is going to be really useful for us. All right, let me show you how to get pH of a basic solution. If I'm going too fast, let me know. Let's say I have the concentration of a sodium hydroxide solution is 0.0752 molar. And I say, well, what's the pH of that? Well, remember, this is a strong base, so if the concentration of sodium hydroxide is 0.0752 molar, that's also equal to the concentration of your hydroxide. Now, in order for us to get pH, we have OH. We need to get POH first. So step number 1 for basic, get POH, and then 2, 14 minus POH is equal to pH. So let's take it. Let's take our calculators and get that POH. So I'm going to go negative log of 0.0752, and my POH, when I do that on the calculator, is 1.12 for my POH. So to get pH, my POH is 14 minus that, so my pH is 12.9. And that makes sense because it's a basic solution, and so it should have a pH that's above 7. So there's some information on pH and POH, and hopefully that helps.